So for today's lecture, we will be discussing definite integral. So we will have the definition of the definite integral and its application and or interpretation. And of course, we will also look at some properties of this that this definite integral possess. Okay, so let's start with this guy here. We recall that if f is a continuous function and non-negative function on the interval AB, then we have this, the limit of the Riemann sum as n approaches infinity. So the Riemann sum, it's the sum of f of x sub I star delta x, I running from 1 up to n. So this limit here gives the area of the region bounded by the graph of y equals f of x, the x-axis, and the vertical lines x equals a and x equals b. So let us recall how we did it. So take note, in here we were considering um, continuous and non-negative functions. Okay, so for example, this is your x-axis, this is your y-axis, and then this is your x-axis, okay, x and y, and suppose this is your function y equals f of x. So take note, continuous, it means you can draw, at least intuitively, you can draw the graph of the function without lifting your pen or pencil, okay? And of course, the actual definition of continuous function, you may recall it from your calculus 1. Okay? So suppose this is your function, y equals f of x. And then this is your a, this is the b. So you have the interval ab here. Okay? And then we take the vertical lines x equals a here, and then x equals b here. Okay? And of course, this is the region that we are interested in. Okay, so the region is the or we have the region bounded by the graph of y equals f of x. So this is your y equals f of x. The x-axis, this is your x-axis here, and the vertical lines x equals a and x equals b. Okay, and let us recall how this guy here was obtained. So what we did last time, okay, was to divide the interval AB into n subintervals of equal length. Okay, so say this guy here, okay, we divide it, okay, and then we label the points. This guy here, it's your x sub 0. This guy here, it's your x sub 1. This is your x sub 2, etc. And then this is your x sub n. And of course, this guy here, it's your x sub n minus 1. Okay? And here we have only few points, but think of it as that there is uh, there is a good number of points in here, in a sense that we have many points. Okay? That is, we have divided this interval into big number of subintervals. Okay? And then suppose we look at this part here as our x sub I minus 1, and then this guy here, it's your x sub I. So that this here is your ith subinterval. Okay? So since we have divided the interval AB into n subintervals, let us denote by delta x the length of the subintervals, and it will be b minus a over n. Okay? Furthermore, the x sub I in here, or the x sub I minus 1, or what, your x sub I this has formula. And the formula is given by A plus I delta X. Delta X is B minus A over N. Okay? So what we did was um, on each subinterval, we chose some sample points. Okay? We chose some sample points, X sub I star. Okay? And in our case, the sample points could either be the left endpoint, or the right endpoint, or we have the midpoint. Okay? In our examples, we did not consider this midpoint, but it's also a possibility. For the left endpoint, okay, it's your x sub I minus 1. For the right endpoint, it's your x sub I. For the midpoint, it's the average of the 2 points here. Okay? X sub I minus 1 plus x sub I divided by 2. Okay? So these are the three good sample points that we can choose. Okay? But you can choose any. You can choose any sample point inside the subinterval x sub I minus 1, comma, x sub I. Okay? And then suppose we chose this guy here. This is our sample point. Okay? This guy here. We look at the image of this sample point on the function. So it's possibly somewhere here. And this guy here has coordinates x sub I star, comma, f of x sub I star. So we evaluate the sample point that we chose on the function. And then we choose this f of x sub I star to be the height of a rectangle with width equal to the um, difference between x sub I minus x sub I minus 1. It's just delta x. Okay? So, in essence, you will be able to construct this rectangle here. Okay? For this um, subinterval. Okay? And then, you do that to all subintervals. Okay? You do that to all subintervals. Okay? For example, we have this subinterval for the first subinterval in here. For the second subinterval, we have something like this. Then for the third subinterval, we have something like this. And then for the fourth, we have something like this, etc. Okay? Okay. And then, of course, for each of these, um, for each of these subinterval, or for each of these rectangle, we will get the area. Okay? So for the ith rectangle, we have your a sub I. This is equal to f of x sub I star times delta x. So the area of this rectangle is given by this formula. And therefore, the region, okay, the area of the region we are interested in can be approximated by the sum of the areas of all the rectangles in here. Okay? But it's just an approximation. Okay? In order to get the actual area, we get the limit as n approaches infinity, meaning we increase. We increase the number of subintervals. We increase the subdivision. Okay? So that this delta x here will be very, very, very small. Take note, as n approaches infinity, you will have your b minus a over something very, 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 very large. And therefore, your delta x will go to 0. Correct? So this is how we did it. Okay? And again, in here we considered continuous and non-negative functions on the given interval AB. Okay? Now, we will extend this formula or expression in here. We will also extend this way of um, deriving this limit here, okay, to functions which may be not continuous, okay, and may be also negative, okay. So let us look at this definition. Suppose f is defined on the interval AB. So in here, your function could be something like this. You have something here and then here. So there's a hole in here, but here there's no hole. Okay. Maybe there's a hole on this part. So maybe there's a hole on this part, but it has a value somewhere else. Okay. So this is your A, this is your B. So this is the interval we are interested in. Okay. So f is defined on AB. It can be, the function can be discontinuous. It's totally fine, just like this. As long as for every number that you take in this interval, it has a value, or you can evaluate it on the function f. Okay? So this could be a possible graph of your function f. Okay? So suppose f is defined on the interval AB. Okay? So what we're going to do is to divide the interval AB into n subintervals, just like what we did earlier. Now, take note of this. We were dividing the interval AB into n subintervals. It does not necessarily to have equal length. Okay? In our discussion last time, we divide the interval into subintervals of equal length. In this case, we don't have that condition. We don't need that condition. So we will divide the interval AB into n subintervals. Okay? And since the subintervals may not have equal length, okay? The subintervals may have different lengths. Each subinterval will have its own representation for the length. So let's just denote delta x sub I, the length of the ith subinterval. Okay? And again, this delta x sub I, for example, you will have your delta x sub 1. That's for the first interval, delta x sub 2 for the second interval, etc. And these two guys here, they may not be equal. Okay? You have the delta x sub 3. These two guys here, they may not be equal. And of course, this guy here and this guy here, they may not be equal. Okay? So the length of the subintervals may not be the same. But what we're going to do is we put this symbol. We put this symbol and then this triangle, and we assign to this symbol the maximum value of your delta x sub I. Meaning, you all have you have values for delta x1, delta x2, delta x3 until delta xn. Okay? And then you will choose the highest delta x there. Could be delta x1 or could be delta x2, etc. So you choose the highest. Okay? Once you have chosen that, you give that to this symbol here. We call this the mesh or the norm of the interval. So the norm of the interval. Okay? Then, let x sub 0, that is your a, that's the a, and then x1, x2 until xn, where xn is your b, be the endpoints of these subintervals, just like the way we did last time. Okay? And then we choose sample points. We choose sample points. xi star, x1 star, x2 star until xn star. So any sample points on the intervals. Okay? So that, of course, x sub I star lies in the ith sub interval. Okay? For example, let's look at this. In this illustration, the function is continuous, but again, it could be anything. It could be um, it could be discontinuous as long as the function is defined on all the points on the interval AB. Now, look at this. This interval and this interval, it's big. This guy here, it's smaller than this, and then you have this. So notice the length of the subintervals, they are not the same. This guy here, and then this guy here. Then you have this guy here, then this small here, and then this guy here, etc. Sorry, not that one, but this guy here, it's longer. Okay, then maybe this guy here, and this guy here. So different length of the subintervals. Okay, if this is the ith subinterval, we look, we get the length of that subinterval and put it as your delta x sub I. So this guy here, it's your ith subinterval, ith subinterval. And the length of this, it's delta xi. Then we choose a sample point. So this guy here, it's your sample point. Okay. And then just like before, once we have the sample point, we evaluate it to the function and then get the rectangle. Okay? And take note, this rectangle here may be different. Well, it will be different, or at least at on the width of the rectangle compared to this, to this, to this, and to all other rectangles. So this is our ith rectangle. This is another rectangle. This guy here is rectangle, etc. Okay. So this is the construction of so far the steps that I have mentioned. So up to this point. Okay. Now we are ready to define what we call the definite integral. Okay. So in here, the definite integral of f from a to b is this guy here. Okay. Now look at this. This guy here, it's read as the definite integral of f of x dx from a to b. Okay. So definite integral of f of x dx from a to b. And this definite integral can be calculated as the limit of the Riemann sum. So this guy here, it's still a Riemann sum. Okay? Summation of f of x sub I star times delta x sub I from 1 up to n. But look at this. We have the limit as the norm. Take note of that. That's this guy here, norm of the interval. As the norm tends to 0. Okay? So the definite integral of f of x dx from a to b, this is the limit as the norm tends to 0 of the summation of f of x sub I star times delta I running from 1 up to n. Provided, take note of this, provided this limit exists and does not depend on the choice of the sample points. Okay? So meaning, you have this guy here, you compute the limit. If the limit exists, then we're good. Okay? And also, in here, we have chosen some sample point in this part. Okay? If if I have chosen another sample point in the same interval, maybe this guy here. Okay? If I get the limit of the Riemann sum, I should get the same answer as in the one I will get if I chose the sample point to be here on this subinterval. Okay? For example, again, on this subinterval, initially I chose this sample point, we do the limit thing, and then I will get an answer. And then maybe later on, I will choose another sample point here, and I get the limit, and then I'll get the same answer as before. Okay? So that's what it meant when it said that this limit here exists and does not depend on the choice of the sample points. Okay? If the limit exists, we say that f is integrable on the interval AB. Okay? Now, again, look at this. What does this mean? This norm here goes to 0. But originally, what is this norm? The norm, it's the largest delta x sub I. Okay? So it is the largest delta x sub I. So if we pass to the limit, if we make the norm, if we push this norm to 0, that will mean the largest length will go to 0. Okay? But what does that mean in terms of the other subintervals? Since they are smaller than the largest, they will be forced to go to 0 also. Okay? And furthermore, when you say this norm goes to 0, so let us look at this. So originally, these were your intervals. Okay? Then if you push that norm to 0, what does that mean? What does that mean? You are actually increasing the intervals. Okay? Because you are making the largest interval to have 0 value or to be as close to 0 value, which means all other intervals will also go to 0. So you are getting smaller subintervals. Okay? And take note, when you do that, for example, originally this is your subinterval, you chose this sample point. Okay? And then you make smaller interval, or you increase the number of subintervals by pushing the norm of your interval to 0. It means you are making, or you are getting, smaller subintervals. But what does this mean? Originally, you only have one sample point here. Then after increasing the number of subintervals, you will have a lot of sample points. You will be able to get a lot of sample points there. Okay? And once your interval is very, 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 very close to 0, it will mean that the sample point will be just, you will have fewer choices of sample point, quote unquote, fewer choices. Okay? So again, quote unquote, fewer choices. So when the largest subinterval, the length of the largest subinterval goes to 0, it will mean that all other intervals will also have length going to 0. Okay? Question? So that's the definite integral of the function f from a to b. So it's this one. This is the definition of the definite integral of f from a to b. Now, if f is defined at a, okay, if f is defined at a, then the integral of f of x dA from a to a, take note of this, from a to a, it will be equal to 0. Okay? If f is integrable on the interval ab, then the integral of f of x dx from b to a, that's equal to the negative of the integral of f of x dx from a to b. What does this mean? If you interchange the location of these two numbers here, you have to take out a negative. Okay? So this guy, integral from b to a. This guy, integral from a to b. So the locations of a and b interchanged. Okay? You take out a negative. Okay? Questions so far? Now, let us discuss more about this definite integral. This symbol here, this symbol that you see here, so this guy here, it's called integral sign. Okay? The numbers a and b, so this guy here and this guy, they are called the upper and lower limits of integration, respectively. Lower, it's below here. Upper, it's the one above here. So lower limit of integration here, it's a. Upper limit of integration, it's b. Okay? This guy here, the integral the integral of f of x dx from a to b, this is a real number. Okay? Of course, you have the Riemann sum, they are all real numbers, you get the limit, you get a real number. If it exists. Okay? If it exists. Of course, if it does not exist, then it's undefined. So if this guy here exists, then this will be a real number. The variable x is a dummy variable. This x here that you see, it's a dummy variable, meaning you can replace it with other letters. For example, the integral of f of x dx from a to b, it's the same as the integral of f of t dt from a to b. So I just replace x with the t. If I replace it again with the s, as long as I have everything the same, except for that variable, then they will all be equal. Okay? So x is a dummy variable. Take note, we are talking about definite integral. Okay? Now, the sum f of xi star plus delta xi, I from 1 up to n, it's still called the Riemann sum. Okay? So this guy here is called the Riemann sum. Now, if A was divided into n subintervals of equal length, now we are here, n subintervals of equal length, then the delta xi will just be delta x. Since they are all equal length, delta x1 will be equal to delta x2 will be equal to delta x3, etc., etc. So since they are all equal, we'll just put it delta x. And then we have the formula. Delta x equals b minus a over n. Okay? And look at this. If they are all delta x, then the norm, this norm here, will simply be delta x. Okay? Furthermore, look at this. The norm goes to 0. Okay? The norm goes to 0. But what does that mean? As the norm goes to 0, it's equivalent to saying, in this formula here, that your n goes to infinity. Okay? And therefore, we have the actual definition from before. Okay? So the integral from a to b of f of x dx, it's equal to the limit as the norm tends to 0 of the sum f of xi star delta xi, I from 1 up to n. It will be also equal to the limit as n approaches infinity of the sum f of xi star delta x. Which means instead of dividing the subinterval, dividing the interval AB into subintervals of random length, we can just divide it to subintervals of equal length, and we will still get the value for the definite integral. Okay? And furthermore, since the value of the definite integral does not depend on the choice of xi star, okay, we can just choose xi star to be either left endpoint, right endpoint, or the midpoint. So we again go back to what we have discussed in the first lecture. Okay? But what's new here is that our function can be anything as long as it is defined on the interval AB. Not just continuous function, not just non-negative. Okay? Question so far? Next, if f is continuous and non-negative on AB, then this guy here, the integral from a to b of f of x dx gives the area of the region bounded by the graph of y equals f of x over AB. So this guy here, okay, with this condition, can now be replaced by the definite integral symbol. Okay? In general, since your function can be negative, can be discontinuous, okay? Your definite integral, if it exists, okay, if it exists, can be interpreted as the net area. Furthermore, the integral itself can be negative. Okay? So for example, your function here, okay, there are negative values for f, there are positive values for f. You still do the same. You still do the same calculation and derivation. You divide the subinterval, you divide the interval into subintervals, okay? You choose sample points. But for example, on this interval here, if you have chosen a sample point to be this part, when you evaluate it to the function f, it will go down here. And therefore, your rectangle, which is this guy here, it's below your x-axis. Okay? The area of a rectangle, it's a positive number. But Since this guy here is below the x-axis, the area will be quote-unquote negative. That's your net area. Again, area by definition, it's a positive number. Okay? But if your function is below the x-axis, then quote-unquote, the area of that rectangle, okay, to be more precise, the net area of that rectangle will become negative. Okay? Mathematically, why? You have your AI. This is your f of x sub I star delta xi. But your function at this point here, it's a negative number. So this guy here will be negative. And of course, delta xi, it's positive. This guy here, it's positive. So negative times positive, this will be negative. Okay? So you do the same process, even if your function is negative. Okay? And therefore, when you pass to the limit as this norm tends to 0, these will be the regions. This guy here, and this guy here. Okay? Now, if your region is above the x-axis, the value of the area, the net area on those regions, okay, will be positive. If your regions are below the x-axis, just like this, the value of the net area of those regions will be negative. Now, if it's a combination, just like this, there are some positive regions, there are some negative regions, the definite integral will be, you add all of this. This guy here minus this guy here plus this guy here. And whatever number you get, okay, that will be the value of the definite integral. Okay? Now, as you can see, it's plus here, it's minus here, it's plus here. So, if you are looking at this, okay, if you are looking at this as your region 1, and then you look at this as your region 2, and then this guy here as your third region, okay? Of course, each will have areas. And in here, our area of region 1, area of region 2, and then you have the area of region 3. These are all areas, and therefore, take note, area is always positive. Okay? But since region 2 here, okay, region 2 here is below the x-axis, you have that minus in here. Region 1, it's above the x-axis. So, well, that's plus here. Region 3 is also above the x-axis. That's plus in here. So this guy here is the integral from a to b of f of x dx. Okay? Are we clear? Questions? Okay. So again, if your function is continuous and non-negative, meaning your function is always above the x-axis or maybe on the x-axis, the definite integral will always be positive because, well, they are all above the x-axis. But if your function is continuous and some are positive, some are negative, then there's a possibility that the definite integral will be negative. Okay? Questions? Now, if your function is continuous, okay? If your function is continuous, then your f is integrable, always. Okay? If your function is continuous, then f is integrable, always. If your function has only a finite number of jump or removable discontinuities, then your function is still integrable. Okay? So, of course, for continuous function, maybe your function is something like this. So, continuous. Okay? For the other case, finite number of jump or removable discontinuities. So you could have something like this. Then here, so there's a jump, there's a hole, there's a hole. Okay? So jump here, removable discontinuities here, as long as those cases are just finite number, meaning um, you can count it. Okay? You can count it. Then the definite integral will exist. Okay? If your function has infinite discontinuities, there is a possibility that your function is not integrable. Okay? That's why it's not included in this part. So again, if f is continuous or if f has only a finite number of jump or removable discontinuities on AB, then f will be integrable on the interval AB. Next theorem here. If f is integrable on AB, okay, then the integral of f of x dx from a to b can be calculated using this limit, the one that we were using in the first lecture. So we can choose delta x to be b minus a over n and your x sub I to be the right end point. Okay? So instead of dividing the subintervals randomly, okay, we can always divide the interval into subintervals of equal length. Questions? So let's work on some examples. Use the definition to show that this guy here is equal to 1/3. Okay? So definition, it means that you will use the limit. Originally, you will have to use this guy here. Okay? But since if this guy here exists, x sub I star, okay, can be anything. delta xi can also be just subintervals of equal length. Okay? So let's do that. In here, you have your A equals 0, your B equals 1. We can have delta x equals B minus A over N. And this is just 1 over N. Okay? And then we use x sub I star to be the right endpoint. That will be A plus I delta x. But A, it's 0. So you just have I times delta x. And therefore, this is just I over N. Therefore, what do we have? Integral from 0 to 1 of x squared dx. This is now the limit as n approaches plus infinity of the sum from I from 1 up to n of f of x sub I star delta x, and this is equal to the limit as n approaches infinity of the sum I from 1 up to n. F, it's your x squared. So in here, so let me just emphasize that your function f of x, this is x squared. So this guy here, we will have I over n quantity squared times delta x. Delta x, this is I over n. Sorry, that's 1 over n. So times 1 over n. Okay? So let's continue solving this. This is equal to the limit as n approaches plus infinity. The sum, I from 1 up to n. Here you have I squared. And then here you have n squared times n. So this becomes n cubed. N here, it's a constant. So it can go out. So limit as n approaches plus infinity of 1 over n cubed. Sum, I from 1 up to n of I squared. But what is this guy here? Try to recall the formula. So we will get limit as n approaches infinity of 1 over n cubed. So let me just write the formula here. Sum from 1 up to n of I squared. This is n times n plus 1 times 2n plus 1 divided by 6. So we put that n times n plus 1 times 2n plus 1 divided by 6. Then you get the limit. Here's a technique that I will show you. Of course, you can cancel one of the n's in here and the n in here. So this guy here will cancel this and you will be left with n squared. Okay? And then you will have now limit as n approaches plus infinity. The 6 here, the 1 over 6 here, I'll just put it outside. And then the n squared, I'll put one of the n's together with n plus 1. Then I'll put the other n, I'll combine it with your 2n plus 1. So meaning I will have n plus 1 over n times 2n plus 1 over n. They're the same. . Following? And therefore, as n approaches infinity, you have here linear over linear. So you just look at the coefficients of the highest powered variable, which is your n. So this is just 1 over 1. In here, you have 2n plus 1. Denominator is n. So as n approaches infinity, you just have 2 over 1. So this will be equal to 1 over 6 times 1 over 1 times 2 over 1. And this is equal to 1/3, which is the one we desired. Question in using this definition? Yes, question?
So is this a situation where you could take like the highest power and then cancel the n3, like I asked yesterday? This
Yeah,
is
yeah, sure.
perfect. Thank you.
You're welcome. Other questions? Okay, next. Express this guy here. So the limit as n approaches infinity of the sum xi to the 4 minus e raised to xi plus xi times cosine xi delta x I running from 1 up to n as a definite integral over this interval. Okay? So in here, what we're going to do is just to convert this to definite integral. But all the information are here. So this guy here will be your function f. This guy here will be the dx. Of course, this guy here, it's your f of xi. And then, therefore, this whole limit thing will be the integral from -2 to 5, that's your interval here, of f of x. So you'll just remove those subscript I on that x. So that you'll just have x to the 4 minus e to the x plus x cosine x, close parentheses, and then this delta x will be converted to dx. So this is the definite integral representation of this limit here. Questions? Next problem here, we want to evaluate the integral of 1 minus 3x dx
Yes, sir.
from, yes?
Sir.
So in here, we want to evaluate the integral from -1 to 2 of 1 minus 3x dx. So we use the definition. We use the definition of this of definite integral. So of course, our f of x, that will be 1 minus 3x. A, that's this lower limit of integration, that's -1. B, that's the higher limit of integration, that's +2. Delta x will be b minus a over n. So this is 2 minus -1 over n, and this is equal to 3 over n. Xi star, this is a plus I delta x. So this one will be -1 plus 3I over n. Okay? So now, let's also write f of xi star. So f of xi star, this is equal to, so you will replace your x here by I star. So this will be 1 minus 3xi star. But your xi star is this guy here. So this is equal to 1 minus 3 times negative 1 plus 3I over n. Let's just simplify this. We will have 1 minus, so minus 3 times negative 1, that becomes plus 3. And then minus 3 times 3I minus 3I over n, that becomes minus 9I over n. Or simply, this is 4 minus 9I over n. Therefore, we have the limit, or we have the integral. We have the integral from negative 1 up to 2 of 1 minus 3x dx. This is equal to the limit as n approaches plus infinity of the sum I from 1 up to n of f of xi star delta x. We have here the limit as n approaches plus infinity of the sum I from 1 up to n. F of xi star, it's this guy here. 4 minus 9I over n. Delta x, this 3 over n. Okay? Then let's continue the simplification here. Limit as n approaches plus infinity of the sum I from 1 up to n. So you multiply this. 4 times 3 over n, that's 12 over n, minus 9I over n times 3 over n, that's 27I over n squared. And then, let us recall sum I from 1 up to n of I. This is equal to n times n plus 1 over 2. Which means, we'll get the limit as n approaches plus infinity. The sum of 12 over n, this n here, this 12 over n here, it's constant relative to the I here. So you'll just get 12 over n times n for that. And then minus, again, 27 over n squared, that's constant relative to I. And then you have the sum of I. This is the sum of I. So this is multiplied to n. It's n plus 1 over 2. Then you can just simplify everything. This is now equal to the limit as n approaches plus infinity. 12 over n times n, that's just 12. Minus, here you have 27 over 2. And then you have this guy here. I'll multiply that. N squared plus n divided by n squared. So we have n squared plus n in the numerator here, n squared on the denominator here. So if we get the limit, coefficient of n squared, that's just 1 in the numerator. Coefficient of n squared on the denominator, it's still 1. So we will end up with 12 minus 27 over 2 or this is equal to negative 3 halves. Okay? Now, let's have some techniques or some properties of these definite integrals. So these properties, uh, they can be derived using the properties of the sigma notation that we discussed. Okay? So in here, if you have the integral from a to b of constant dx, so see here it's a constant, then this definite integral it's just equal to c times b minus a. Okay? So for example, integral from negative 2 to 5 of 3 dx, this is just 3 times 5 minus negative 2. So this is just 21. So 3 constant. Your a, it's negative 2. Your b, it's 5. So b minus a. 5 minus negative 2, that's 7. So 7 times 3, that's 21. Okay? If you have the integral from a to b of f of x plus or minus g of x dx, provided the integral exists, okay, then you can distribute this integral sign. Integral of f of x dx from a to b plus or minus depending which sign you use here, okay? Integral of g of x dx from a to b. So meaning you can distribute this integral sign. Again, provided that the integrals exist. Meaning you have an answer for this and you have an answer for this, or you have a value for this, you have a value for this, then you can do this. Okay? If you have a constant times a function, you have, and you want to integrate that from a to b, then the constant can just go out of the integral sign. So just calculate the integral here, then multiply it to the constant. Okay? Now, look at this. This is a technique that I'm going to add in here. You have the integral of x to the n dx from a to b. This will be equal to b raised to n plus 1 minus a raised to n plus 1 divided by n plus 1, provided your n that's not equal to negative 1. Okay? So, for example, you have the integral from negative 1 up to 3 of x cubed dx. According to this formula, okay, according to this formula, you will have 3 to the 4 minus negative 1 to the 4 divided by 4. And then you just simplify this. Okay? Other questions?
Yeah, I'm just wondering what the difference between what you just explained for like the x squared example and the other formula.
Next, the integral of f of x dx from a to b, this is also equal to the integral of f of x dx from a to c plus the integral of f of x dx from c to b, provided all the integrals exist. So in here, this is one of the illustrations. So on the left-hand side, you have the integral from a to b. On the right-hand side, you have the integral from a to c here, and then the other one is the integral from a to b. So you can combine them, or you can chop the interval into two parts, and then get the integrals on each subinterval after you chop it. Okay? Now, here's the good thing to this formula. Even if your C is not in between AB, this formula still holds. For example, suppose you have this function here. Sorry, you have this function here. This is your A, this is your B, and your C is here. Okay? The, the integral on the left, it's just this guy. Correct? The integral on the right, it will be from A until C. So what will that be? So in here from A until C, it will be from this up to this. So you will have this region. And then of course the integral in this case from B up to C, you will have this region here. Correct? Let's analyze this. On the left, you have the integral from A to B, f of x dx. On the right, in here, okay, in here, you have the integral from A until C of f of x dx, and then plus the integral from C to B of f of x dx. Correct? But what is this integral from A to B, f of x dx? It's this red part. To get this from the integral from A up to C, you have to subtract this black region here, correct? So your red region, that's your left-hand side. The purple region, that's everything in here. The black region here, it's just from the integral, it's just from the interval B to C. But look at this. Look at this. You have C to B. On this interval, you have B to C. So if I interchange the two guys here, if I interchange that, B to C, f of x dx, remember the definition? I have to put out that minus. I have to place that minus. And now, you see, it's consistent. Integral from A to C, f of x dx, minus the integral from B to C, f of x dx. So the purple minus the black, that's your red. Okay? So what I'm saying is, your C here, it can be anywhere. It can be after B. It can also be before A. Or it can be in the middle of A and B. Just like this guy here. Okay? So the arrangement of A, B, and C here can be anything. Okay? But here, how are you going to look at this so that you will remember this easily? You have the integral from a to b. Okay, that's your left-hand side. On the right-hand side, you have the integral from a to c, integral from c to b. Okay, so a up to b. Okay, so I hope this guy here will help you remember how you're going to use this formula. Now, if your function is non-negative, okay, so if f of x is greater than or equal to 0 on the interval a, b, then the definite integral will also be non-negative. So the definite integral of f of x dx from a to b will also be greater than or equal to 0. If you have a function f of x and a function g of x such that f of x is greater than or equal to g of x for x between a and b, then the integral of f of x dx from a to b will also be greater than or equal to the integral of g of x dx from a to b. Okay? So for example, in here, you have your function f of x in here. Your function g of x is lower than your function f of x. Of course, in this case, both of them are non-negative. So you will clearly see that the area covered by your function f of x, okay, over the interval ab is greater than the area covered by the function g of x covered over the interval ab. Okay? And again, this illustration, your function f of x and g of x, they are both positive, but they can be anywhere in your plane as long as your f of x is greater than g of x. Maybe your function f of x is somewhere here, and then your g of x is somewhere here. Okay? This will still hold. So as long as your f of x is greater than or equal to g of x over a certain interval, then the integral over that interval, okay, of your f of x will still be greater than or equal to the integral over that interval of the g of x. And because of this, suppose your f of x is bounded above by constant capital M and bounded below by constant small m over the interval ab, then if you calculate the integral of f of x dx from a to b, it will also be between these numbers here. M times, so capital M times b minus a, that will be greater than the definite integral. Then small m times b minus a, that will be less than the definite integral. Okay? And this guy here, it can be interpreted using this way. So capital M, this is always greater than your function f of x. Small m here, that's your smallest value of your f. So this dark purple here, or this purple here, it's your rectangle with height small m and width AB. Okay. And then this sky blue or light blue, or maybe sky blue, together with this purple, that's the region bounded above by your function f. And then this very light blue here, okay, that's part of the rectangle with height capital M. Okay? But this guy here can be proved easily. since you have f of x greater than or equal to small m but less than or equal to capital M, so you have this, and you have this, you can integrate this over AB. And the equality or the inequality remains the same, correct? The inequality remains the same. AB dx. But M is constant. Capital M is also constant. And our formula, if that's constant, it's just M times the length of the interval, which is B minus A. So you have that, and then also in here you have capital M, B minus A. So we are just combining the properties that we know so far. Okay? Questions? So this particular property here, we can use it to estimate the value of this definite integral. If we cannot solve it yet, we can just use some estimation. Okay? For example, let's give an estimate for the definite integral of 1 over x dx from 1 up to 2. Okay? So your interval is 1 comma 2. Your 1 over x will be between 1 half and 1. Correct? If your x is 1, then you have the 1. If x is 3 halves, then 1 over x will be 2/3. If x is equal to 2, then 1 over x will be 1 half. So this is what we know. Therefore, the integral from 1 up to 2 of 1 over x dx, this will be greater than or equal to 1 half times 2 minus 1, but less than or equal to 1 times 2 minus 1. But 2 minus 1, it's just 1. So the integral from 1 up to 2 of 1 over x dx, this will be less than 1, but greater than or equal to 1 half. So this is an estimation. Okay? Questions? Another example here. Given that the integral of f of x dx from a to b equals 12, and the integral of f of x dx from a to c equals 5, find the value of the integral from c to b of f of x dx. Okay? This is what we know. So we know the integral from a to b of f of x dx, we can decompose this into the integral from a to c of f of x dx plus the integral c to b f of x dx, correct? We want to find the value of this guy. So this guy here. Given that we have a value for this, that's this part here, and also for this, which is this part. So we can just solve for this. This means that integral from c to b of f of x dx. So we bring this to the other side of the equation, so you will get minus. This guy here remains on his side of the equation. This guy remains on his side of the equation. And therefore, here we'll have the right-hand side to be integral of f of x dx from a to b minus integral of f of x dx from a to c. But this guy here, it's equal to 12 minus this guy here, it's equal to 5. So this is just equal to 7. Okay? Questions? Next. Evaluate.
Sir?
Uh-huh. So here we want to evaluate the integral from 0 to 2 of square root of 4 minus x squared dx. Now this guy here, this is a bit tricky. Okay? But I'll give you the trick on how to solve this. So for now, we will do this way. This is your function f of x. Okay? So you have the function f of x. You have the function f of x equals square root of 4 minus x squared. And then you can think of this guy here. Square y equals 4 minus x squared. And then you can manipulate this. You will have y squared equals 4 minus x squared, or simply you will get x squared plus y squared equals 4. So this function here, this represents a portion of your circle. Particularly since you have positive square root of 4 minus x squared, you will have a portion of the circle that is above the x-axis. Okay? So this guy here, it's a circle of radius square root of 4. So it's a circle of radius 2. Okay? So here you have 1, 2, 1, 2, 1, 2, 1, 2. Now, your function f of x equals square root of 4 minus x squared. Like I said, it's a portion of the circle that is above the x-axis. So somewhat you will have something like this. So pretend that this is a circle, okay, of radius 2. And then you are only considering this guy here. Moreover, you only want the interval 0 to 2. So you just want from this point up to this point. So your f of x is simply this part of the circle. Okay? So this is your f of x equals square root of 4 minus x squared on the interval 0, 2. Okay, so far? Now, your function, it's positive on this interval. So this guy here, this definite integral here, this is simply the area of the semicircle actually the quarter circle, okay? Quarter, or the area of the region bounded by area of the region bounded by the quarter circle over the interval 0, 2. So I'll just write it as bounded by the graph of y equals square root of 4 minus x squared over the interval 0, 2. But then again, this is circle and we know a formula for the area of the circle. So note area of circle of radius r is pi r squared. Radius here, it's equal to 2. And we only want quarter circle, this slice. Therefore, the integral from 0 to 2, square root of 4 minus x squared dx, this is just pi times 2 squared divided by 4. You just need this slice here. And this is equal to pi. Without doing the definition, we were able to calculate this guy here. Okay? So that's all for today's session. Thank you for staying, and I hope to see you next meeting.